Buenos días a todos. Vamos a ir empezando, ¿vale? Good morning, everybody. It is a great pleasure. No, let me use my glasses. I cannot see anything. It is my great pleasure to introduce you our guest speaker, Professor Nitin Padture. Professor Padture is Otis Randall University professor in the School of Engineering at Brown University, where he is also founding director of the Initiative for Sustainable Energy. Over his career, he has held several leadership positions, including director of Brown's Institute for Molecular and Nanoscale Innovation, distinguished professor at the Ohio State University, where he also founded and directed the Materials Research, Science and Engineering Center. And earlier, he spent 10 years on the faculty at the University of Connecticut. His research lines include the fields of advanced ceramics, semiconductors, and nanomaterials, with applications ranging from jet engines to solar cells. And he is the author or co-author of over 300 scientific publications, which have been cited about 45,000 times, with an index of 102. He is also a fellow of the American Ceramic Society, the American Association for the Advancement of Science, and the Materials Research Society. He received many honors, including the Robert Cobell and Richard Fulrath Awards from the American Ceramic Society, the Presidential Faculty Award from Brown University, and the prestigious Humboldt Research Award from the Alexander von Humboldt Foundation. He is also editor of the leading journals Acta Materialia and Scripta Materialia. And also, he happens to be my postdoc supervisor. I was working in his lab for 2 years, 20 years ago. It was a great time and experience. He was the one who introduced me to the fascinating world of advanced ceramics with nanomaterials. And definitely that experience marked me as a scientific and also as a person. Today, he will talk to us about the promise of Halide-Perovskite solar photovoltaics, and I hope also about advanced ceramics, a little bit. And I'm pretty sure this talk will be very inspiring to all of us. Thanks.
Okay, can you hear me? Yes, thank you. Again, whenever I give talks in Spain, I always apologize. I have to give my talk in English, but someday maybe I will give it in Spanish. But it's really a great pleasure to be back in Sevilla. And as Rosalia said, she worked in my lab for 2 years, and I have some photos at the end. Not embarrassing, but but what I want to emphasize is that she has not changed a bit in 20 years. All right, so I'm going to talk about halide-perovskite solar cells. And first, I'm going to talk a little bit about the perovskites themselves. And I consider them to be ceramics. They're just not very good ceramics, very poor mechanical properties, but they have great optical properties, which is why we are using them as solar cells, right? And so whenever you look in material science, there's never perfect material for one particular thing, okay? So you have to always compromise. And so you focus on those best properties that the material has, and then use innovation to get around the other constraints in order to make that material work in a device, right? Anyway, so I'm from Brown University, which is in the northeast corner. It's in Providence, Rhode Island, which is about 1 hour south of Boston and about 3 hours from New York. And it's one of the oldest universities, not as old as some of the universities in Spain, but old by United States standards. So this is the outline of my talk. I'll talk about the rationale, why we are trying to do this, And hopefully I'll inspire you to think that solar is really the future, and anything that you do in solar, any innovation, is actually very worthwhile, right? And then I'll tell you basically two stories. One is about mechanical behavior and how it actually relates to the performance and stability and the durability of these devices. And second story is about flexible solar cells, which are made on plastics or flexible materials, and how we discovered a new mechanism which will hopefully help us improve the durability of flexible solar cells and why we use them. And then end with some outstanding issues. What are the issues that are outstanding, and hopefully that can inspire some of you to maybe look at this materials of this field. Because myself, I came from ceramics field all my life. I was mostly mechanics of materials and ceramics and processing and so on. And I did not know how a solar cell worked until 2020 and 2012. And I jumped into this field. And so as you can maybe tell that I still don't know quite about how solar cells work in some areas, but we are making contribution. You can bring something new to the table. And that's very important. That's very unique, right? All right, so why are we trying to do this? And I think you may have seen this chart somewhere over here. So this is finite sources. And the problem is that these emit CO2, which are greenhouse gases, which is causing climate change. And we are coming to a tipping point where climate change is not sustainable. And these are renewable sources, and you can see the amount that is produced. But solar is this yellow circle. So it's really a limitless supply of solar energy. And many of the other energies are actually derived from solar. And the wind blows because of the difference in the gradient in the pressures because of the sun. Same thing with tides and everything else, right? And so, but this is what's happening in solar. So this is the global electricity capacity, and this is a chart from Science magazine. And so you can see, obviously in this chart, where you should be working in. And this is solar, which is really accelerated in deployment, right? And so today we have reached over 2.5 terawatt global installation in 2025. So it's been exponential growth in terms of growth compared to other energy sources, right? And so that's where the excitement is, right? Then cost. So people think that solar was, it's very expensive. It used to be 10 times more expensive, more than that. But now we cannot complain that solar is expensive, because actually cheaper than gas, cheaper than coal, cheaper than everything almost, right? So this used to be $360 per megawatt hour. Now it is $60 per megawatt hour. And the United States goal is $20 per megawatt hour. At least that was the goal when we started working on this. Maybe it'll come back to that goal again, right? But that is the situation, right? And so Science magazine declared solar photovoltaics and renewable energy as the breakthrough of the year for 2025. So this is where the excitement is, and you have to be working in a field which is growing, not dying, right? Obviously, I don't need to say that, but this is where the excitement is, and any contributions that scientists, material scientists, ceramics people can make is actually going to be very worthwhile. In terms of Spain, Spain is actually leading the way. So this is annual installations, and this is the total energy capacity. So Spain has reached 40 gigawatt total installed capacity. And Spain happens to be one of the rare countries where solar photovoltaics is actually the largest source of electricity among all other sources of electricity, right? So that's very exciting as well. Now, of course, sun doesn't shine at night, and therefore you have to have solar storage. I think everybody knows, and some of you are working on it on this field. And so if you just look at batteries, the cost has been coming down to about $100 per kilowatt hour storage. That is really a breakthrough. We never thought it would happen, because it started at $1,200 per kilowatt hour. So that is amazing development. And the capacity is growing exponentially. And so these are all coming together, solar and batteries and storage, right? And so, for example, California in the United States is leading the way. And so every day they publish this chart. So this is 100% need, and part of the day, more than 100% of the need of entire state of California, which is bigger than some countries in Europe, is supplied by solar. And then, of course, in the evening, the batteries kicking, these are the batteries, and whatever is white, We use gas power for this is actually one of the most popular days in California, the Super Bowl Sunday, football game, as you know, right? So this extra population there, maybe 2 or 3 million extra people are in that state, right, that day. And so this is very, very exciting, right? And so there are some predictions that say that we reached about 2.5 terawatt of installation around the world, but we will need about 75 terawatts by 2050 if we are to achieve the COP21 goal of limiting it to 1.5 degrees Celsius. And so by 2033, it is likely that solar will dominate the production of electricity. So what I showed was installed capacity, but production of solar will basically be dominating by 2033. And so if your life depends on solar energy, if the economy depends on solar energy, the world depends on solar energy, we cannot be satisfied with the current technology. There's going to be insatiable demand for innovation, new technologies, because this happened in computers, for example. Computers are essential, and that's why memory has become exponential. The cost has gone down exponentially. So everything becomes, innovation takes place when there is this tremendous need, and your life and your economy depends on it. So that is my pitch, is that solar is really a great field to get into, and you cannot be satisfied by the established technologies, say silicon, for example. There always will be need for new things which are yet to be discovered. So we don't know what new things will happen if all these great minds can come together, right? All right. So with regards to solar, as I mentioned, the cost is really coming down. So this is the module price, and so this is 1970s. It was more than $70 per watt, right? And then this was the prediction in 2010. So this is published in 2010, and basically this has been achieved. So today you can buy solar panels that are about 25 to 30 cents per watt, right? It came down from $70 per watt, right? But here is where we want to go. We want to go to pennies per watt, 1 or 2 cents per watt. And so in order to get there, you have to have earth abundant materials in this solar cell. You cannot have precious metals, otherwise you cannot decrease the cost. You have to have small amounts of material. You cannot have large wafers or bulk materials. You have to use minimum amount of material, even if it's earth abundant. Cheap to make. Solar silicon is basically melted. Melting point of silicon is 1425. So it has to be molten at 1600 degrees Celsius and cast into single crystals, right? So there's a lot of energy that goes into it. There's a big carbon footprint. And so if you make solar cells at near room temperature, that is, you're winning the game. You're reducing the amount of energy you need to make the renewable energy devices, which is very important. And then, as I mentioned, small carbon footprint. And the efficiency has to be high. Because if you look at the Shockley quasar limit, for single junction solar cell, the theoretical limit, the absolute theoretical by physics, is 33%. The solar cell that you can buy, best ones are about 25%, regular ones are about 20 to 21% efficient. Yes, solar energy is free, but then you have to use this large area in the world in order to collect that energy and convert it into electricity, correct? And so the efficiency inherently is actually quite low, and therefore if you reduce the efficiency of the solar cells by new technology, which may be cheaper and all these other materials, you have to use more real estate. So we cannot compromise in efficiency, right? So this is the chart of laboratory scale record efficiencies. And you can see this is silicon is basically flat. Gallium arsenide is one of the highest, but it's very expensive. Typically used for satellites and things. And then this is heterojunction. And these are the emerging photovoltaics. This is dye-sensitized, organic, and quantum dot, and so on. And so this is where perovskite came in. And you can see why there's this excitement in this field, is that it went from about 4% to today at 27.6% efficiency, which is about the same as silicon, right? And you can see that this is a thin film material. So this is silicon wafer is about 200 microns. This is half a micron. 500 nanometers is all you need for all the absorption of the solar spectrum. And you can produce electricity, right? And also, if you look at the payback time and carbon footprint, it is much lower than silicon, right? And so this perovskite basically has the potential to satisfy all the requirements for this new type of solar energy for pennies per watt in potential, right? And by the way, so if you actually combine perovskites and silicon, which is called tandem solar cell, because silicon is fixed band gap, 1.1 eV, it absorbs only a certain part of the solar spectrum. That's it. It's actually not a very good solar material. But you can actually add this perovskite, which can be tuned in order to maximize the efficiency, right? So it can go up to 35%, right? And so with the new technology, you're not just replacing old technology. By virtue of this new materials and new technology, you have new functionality. It's different. It's not exactly the same. It doesn't fit in the slot. It has its own new properties. And so you can use this for this tandem, as I mentioned, so on top of silicon. And then since these are thin film materials, 500 nanometers deposited at near room temperature, you can put it on plastic, lightweight for drones, tents, deployable solar cells. Then you can actually tune the band gap and you can make it building integrated. So you have a wall which is basically collecting sunlight, producing electricity, and it's all looking beautiful. So you can do that. You cannot do it with silicon. Silicon is ugly black, right? And then in space, also they're radiation tolerant. So for example, silicon is a stone, it's a rock, a gallium arsenide. When it gets damaged by radiation, atoms get displaced, but they're stuck there. So that's a permanent damage. These are dynamic solar cells. They may not be as efficient as gallium arsenide, but when the sun is not shining or when the satellite is facing the other direction, it can heal and the atoms can go back to their original position. It can recover. So there's a lot of excitement in perovskite solar cell for for space applications. And so I'm actually advising a student group, there's a completely undergraduate student group that is building a CubeSat, and NASA is going to launch this with perovskite solar cell into the space to study how solar cells behave in space. And it's really very proud of what the undergraduate students are doing. So they're designing everything, including the CubeSat, the electronics, the avionics, and it's amazing. Anyway, so for people who are not familiar with the perovskite structure, so when the students here and postdocs here, so this is the structure AMX3. This is the 3D structure, and M here can be lead or tin. Then you have X, so instead of in ceramics is typically oxygen, but here we have halide, so that could be iodine, chlorine, or bromine. And then you have this A site in this cage, and this cage is actually quite large, and so none of the monovalent cations can fit in there. They rattle. And as anybody know from beginning ceramics crystal structures, you cannot have rattling atoms inside a structure. It has to be snug, right? And therefore, cesium barely makes it. Francium, of course, will make it, but it's radioactive, so you don't want to use that. And so therefore, you have to actually use molecules, cationic molecules, in order to stabilize the structure. And one of the popular ones is methylammonium, and the other one is formaldymedium. So for ceramics people, it's very fascinating that you have an organic molecule that's actually rotating. And when it sits there, it doesn't stay like an atom. It spins, right? And you have a crystal. So it's very different for ceramics people to think about these structures. And that took me a while as well. But these are very fascinating materials called hybrid or inorganic organic, right? And so that would be a typical composition we would use, FAPBI3 or formaldymedium lead iodide, right? And so there's hundreds of compositions, as you can see. There's lots of combinations here, right? But also, this is the specialty I showed you, but we can actually have what are called two-dimensional perovskites. So you can have layers, one layer or two layers or three layers that are bonded by organic ligands. And so these are called Dion-Jacobson or Mordelsson-Popper phases, right? And it turns out that this is only on this line here. So this is 3D, this is 2D. You can also have 1D, you can have 0D, and then you can have these what are called perovskitides. And so the family is massive. You have millions of compounds you can actually have. And so it's really a big playground, especially for people who are doing AI and ML, machine learning. This is really fascinating because we don't know many of these compounds. We don't even know they exist. We don't know whether they can make it. but you can actually discover some interesting properties in this space, which could be the next best solar cell, for example. So that's the story, right? So why do these work in perovskite solar cells? Why is the efficiency so high, right? And this will happen so fast. So gallium arsenide took decades because they had all these problems. And the reason is, first reason is they're excellent light absorbers. So this is solar spectrum. This is silicon, and this is log scale here. So as you can see, silicon is a lousy solar material. It doesn't absorb light very well. This is gallium arsenide. So gallium arsenide is like Ferrari of your solar cells. And this material is actually better than your Ferrari at the cost of a Peugeot, okay? And so that is the situation. So you can make kind of quick and dirty solution process film, and you can get more absorption than gallium arsenide. And that was a puzzle in the beginning when people started working on this. So I was involved in a lot of the early thinking in the beginning. And the reason is that the defects that form in these crystal structures, the point defects that are energetically favorable, are very shallow. They're either close to this level, the valence band, or the conduction band. None of these defects that are called deep defects are not energetically favorable. So this is like gift from God. That in this gift of nature. Let's make it secular. It's a gift of nature that we have these this phenomena that the defects are actually very benign, and that's why you don't need to actually perfect the film, and it can still absorb light very well, right? And so there are different kinds of device structures. So for example, this is a NIP structure. So this is basically 5 layers. So you have the transparent conducting electrode, light comes in this way, then you have a N-type layer, absorber, P-type layer, and then an electrode. And so this is a structure, the TM pictures from my group, early pictures that show the cross-sectional structure. So light goes in, you create electron hole pairs, and then the holes can go this way, electrons can go this way, and deeper inside you get more. And then the holes cannot go this way because it's an N-type conductor, and then the electrons cannot go this way, and therefore you can collect current, and that's how basically the solar cell works, right? And of course, the understanding is still evolving actually, right, after so many years. And so there are a variety of these structures. This is called mesoscopic, where you have, instead of a N-type just flat layer, you can have mesoscopic. So you can have a composite here, and this is a flat layer, and this is upside down. So this HTL, or the P-type is on the bottom, and N-type is on top. And they have different advantages and disadvantages. And then when you have tandem, you can have 4-terminal, where these are 2 separate solar cells on top of silicon. And this is what is called a 2-terminal tandem, which is on top of each other with a interconnection layer. All right, so processing of these films is actually quite easy. So these are hybrid materials, and their formation energy is quite low. The melting points are very low, and they can dissolve in ordinary solvents, clear solution you can make. And then you can deposit them using what are called beakers and benches approach, right? And you can continuous deposition. So for example, we do spin coating, and you can see this beautiful microstructure. Looks like a ceramic, right? Grain boundaries in aluminum oxide. If I showed this to you and said this is aluminum oxide, you would believe it, right? Or barium titanate. And then this is the cross section. So you typically need about 500 nanometer film. More than that, it becomes parasitic. So 500 nanometers absorbs all the light that you'll need because it's such a good light absorber, right? And so the whole solar cell active is 1 micron. That's really amazing. There's hardly any material needed, and it still gives you efficiency the same as silicon, right? And so there are different. So there's a lot of work going on in different scalable methods. You can use gas, you can use vapor, you can use spray, slot die, blade coating, and then you can deposit all these layers. This is a production line for rigid solar cells on glass substrate, or you can deposit on polymers, and you can have roll-to-roll continuous manufacturing, right? And so it's highly scalable and low capex is capital investment, low capital investment. All right, so the first story I want to tell you is, so that was sort of a background. First story I'm going to tell you is about mechanical properties of rigid solar cells and its connection to durability, because that's one of the problems. Efficiency is great, but these materials, as I said, are on the cusp of stability, right? That's why they're easy to make at room temperature, but they're also easy to break. They're very easy to destabilize. So that's where the innovation lies, is to take advantage of easy to make, but then make it difficult to degrade or make difficult to break, right? So that's where the innovation lies. So anyway, so you have multiple layers, and they have diverse thermomechanical properties, and therefore you end up with the residual stresses that can be as high as, say, 50 MPa, megapascals. And thermal cycling, these have to be tested from minus 40 degrees, so it's like Siberia. 85 degrees, that's Andalusia, right? And then in space, it's minus 200 to 100 degrees Celsius, so that range is huge in space thermal cycling. So the stresses can be even higher, 80 MPa up to 200 MPa in tensile stresses. And then if you make flexible solar cells on plastic substrates, the stresses can be even higher, about 300 MPa, right? And the problem is the stresses would be okay if the properties of these materials were good. But the properties of materials are really bad. I mean, the toughness is low, so they break if you look at them the wrong way, right? So you don't even need to apply stress. Their hardness is low, the stiffness is low, and the interfaces are very weak, and so they fall apart. So my ceramics friends laugh at me. They say, "Why are you working on this?" And I worked on structural ceramics, highest toughness composites, and so on. But the reason we are working on it is because they absorb light like crazy, right? Ordinary ceramics don't do that, right? This is very unique materials, and therefore we have to solve the other problems in order to take advantage of this, right? All right, so my famous photovoltaics colleague basically said that if solar cells don't work, they fall apart. So that's my job now, is to bring in the ceramics and mechanics expertise to try and address this problem of reliability, right? Okay, so a tutorial for people who may not be familiar with mechanical properties. So you basically have offense, that is stresses, and you have defense, this is the properties of the materials, right? So you always have this competition. Obviously, the properties win, which is why I'm standing here, the floor is not falling, the ceiling is staying, right? But eventually, the mechanical properties degrade over time, or cycles, and the stresses can either build up or they can relax. And so where they meet is where failure occurs. And it's stochastic because we don't know when it's going to happen, because there's so many different considerations of how it's degrading, how the stresses are building, and where the weakness is, and so on. And therefore we use, I'm not going to go into the details of this, but that's why we use Weibull statistics, like weakling statistics, to do this, right? And so we study reliability and durability. All right, so when we started working on this, the most basic property, which is Young's modulus, was actually not measured. So it's like starting an optical materials project without actually knowing what the band gap is. So that's the first thing you do, is to measure the band gap. So first thing you want to do is measure the Young's modulus, right? And so we made single crystals. You can actually make single crystals very easily in the sense that at room temperature, but with some expertise. But you just leave it in the beaker for a week, and you make beautiful centimeter-sized crystals. And so we did direct measurement using stress strain in compression, and measure the Young's modulus. For example, this is MAPB BR3, and this is iodine 3. And this is about 13 GPa, it's about 11 GPa, compared to silicon, which is about 160 GPa. And by the way, the reason why this is stiffer is because of it basically is controlled by the lead-bromine bond. And that bond distance is smaller in the case of bromine compared to iodine. That's why it's stiffer, this material. That's the work of my former PhD student. And then we measure toughness. So indentation is very familiar to everybody. So toughness is single crystal. And so the toughness you can see, these are depressing numbers. This is 0.1, this is 0.14, silicon is 1, something like titanium is 50, right? And so these are not very encouraging numbers. And this is in terms of energy. And then the hardness also is very, very soft. They're like salt. These are salts, right? They're halide, like table salt. You can crush salt very easily. And so this is 0.15, 0.3, this is silicon is about 14, alumina is about 19, diamond is 40, right? Anyway, so that's the story there. And so if you look at this and put these on these Ashby map, you will see that they're sort of in the white space. So they don't fall in this any particular category. They are very unusual combination of properties. So for the material scientist, it just makes these materials interesting just from the science point of view, whether they're solar cells or not. It's because fascinating combinations. Why are they here? Why are they not among any of these things, right? That's very fascinating. Anyway, so we have residual stresses, and then we have the material properties. By the way, we measured the properties of thin films as well, but I don't have time to talk about that. But you have these residual stresses, which can be amplified if it's bending. And then you can have cracks, there are always cracks, and these stresses act on those cracks. When the cracks are critical size, they will propagate, and you get what are called channeling cracks through the thickness of the film. These cracks by themselves are actually not a problem because they're very thin, and so the area reduction is maybe 1%, because the carriers, the electrons and holes, are going up and down, so they don't care where this crack is, right? It's only loss of only 1% area is nothing. But from a mechanics perspective, if you know your mechanics, thin film mechanics, when you have a free surface, you can produce interfacial cracks. So for an interfacial crack, you have to have a free surface. And the free surface is at the end here, but let's say if you have a meter square film, then that's very thin. The crack can be only there. There's no cracks, interfacial cracks there. But if you have a series of these vertical cracks, you can form interfacial cracks. That is kiss of death for the solar cell, because the carriers now cannot glow. They're blocked, right? So these vertical cracks are like a catalyst for the interfacial cracks, because they provide an array of internal free surfaces, right? And so we need to prevent these. But if you cannot prevent these, because these are very brittle materials, and you cannot really use composites and things. For example, if you put carbon nanotubes, forget it. You cannot. It has been fine-tuned. You put anything in there to try and toughen this, it's going to kill the properties, right? And so what we thought is that we cannot prevent this, so why don't we toughen this interface? Okay. You can put super glue there, it'll be perfect, but solar cell is dead, right? Because it's also so fine-tuned. And so what we started working on is using what are called self-assembled monolayers, and many of you may know this, self-assembled monolayers. And so this is a very famous self-assembled monolayer called silane, which is used in fiber reinforced composites. So all fiber reinforced composites, it's sold by the tons. Silica fibers are covered with a silane SAMs, and then it's embedded in the polymer, because then you get the bonding between the fiber and the polymer for stress transfer, right? Our innovation here was to terminate this with iodine, and it's called iodinated self-assembled monolayer. Also, it's short chain, it's cross-linked, right? And then we measure the toughness using a what's called DCB technique, double cantilever beam. You find that when you put the SAMs, the toughness goes up by about 50%. Because of this anchoring of this and the anchoring of the iodine into the metal halide perovskite. MHP is the metal halide perovskite. And so we work with a colleague who does DFT modeling. And so this is the iodine termination of the SAMs, and that's the perovskite. And what we discovered is actually has two kinds of bondings. One is the iodine in the SAMs bonds to the undercoordinated lead in the perovskite. And then there is a halogen-halogen bond between the iodine in the SAMs terminal group and the iodine in the perovskite. So you get both effects, right? And so what happens is the halogen bonding actually decreases as you go to a different halogen. So for example, if you use bromine, then the toughness goes down. And then when you terminate it with hydrogen, then it actually becomes almost like there is no SAMs there if you terminate it without the halogen, right? Anyway, so by putting the SAMs in there, but the SAMs also doesn't kill the properties of the solar cell. It actually makes it better. And so here's the solar cells with no SAMs, hydrogen SAMs, and iodine SAMs. This layer here, and you can see this is the photovoltaic property. This is what is voltage, and this is current density. Many of you may not be familiar with how to read this, and so this is called open circuit voltage. VOC is open circuit voltage. So you want to maximize this, and this is called short circuit current. You also want to maximize this. And this is what's called the fill factor. And the fill factor is how square this curve is. So you want that curve to be as square as possible. Then you have a very efficient solar cell. But this is like a seesaw. So if you increase the band gap, your open circuit voltage increases, but then you absorb less light because your band gap is bigger. And therefore, the JSC goes down. Right? So it's like a seesaw. And so for students or postdocs or whoever wants to, I put together this animation to understand solar cells, how they work. So you can think about it in the terms of water. So this is basically rain or sunlight being collected in a tank, right? And so the VOC is the potential. That's what's called the head, right? And then this is JSC is what is called flux, okay? And so, for example, if you decrease the band gap, then your JSC, your flux increases, but your head decreases. If you increase the band gap, then your JSC decreases, but your head increases. So that's always a seesaw compromise. And so if you have friction, then you get loss of JSC, what is called scattering. And if the tank is leaking, you get loss in VOC, right? And so you don't want any of these, right? And so you open the tap and you turn the turbine, that's your flux, and this is where the power max comes. Maximum power occurs at the maximum of that curve. And whatever water doesn't come on the turbine spills is your FF. So you want all the water to go on the turbine, but practically not possible, right? With the devices, right? So that's how the solar cell basically works and how we can play with the band gap and FF and friction and so on in order to maximize the efficiency of these solar cells. All right, so this is what is called stability. So we basically use the maximum power points. It's a very severe test because normally solar cells don't operate continuously for thousands of hours, right? Work for 12 hours, sometimes 14 hours in summer, and then it becomes dark and then it can relax, right? But this is a very severe test, and what it shows is that if you don't put the SAMs, if you don't toughen the interface, then the TAT, which means loss of efficiency by 20%. So it retains 80% of its efficiency, that's the time, is about 700 hours. And when you put the SAMs, these are 3 different devices, can go up to 4,000 hours, right? Sorry, this should be 1900 here. So it's 4,000 hours, right? And so if you look at the solar cells after testing, you take it apart and you look at it, you'll find that there is voids and delamination. And then when you, I won't go into this, but when you have the SAMs, you can see that after the testing, the interface is relatively pristine, which is why the solar cell is lasting longer. To me, as a mechanics person, it makes sense, right? If you make the interface tougher, it's going to be difficult for it to come apart during the operation of the solar cell because it's a dynamic solar cell, not like silicon. Silicon, this would not be a problem because nothing is moving. And so this approach would not work in silicon. So it works only in this system. Anyway, so that's the connection, all right? And then we did things with the mesoscopic, the toughness is even higher, the efficiencies are even higher. Same story with the stability. And then you reverse it, make it upside down, PIN structure, and you put another different kind of SAMs called carbazole phosphanic acid SAMs, and the toughness here even higher, and the efficiency. And also, we adjust what's called the dipole because it's charged SAMs, and it results in efficiency that are even higher, 26%. So the record is 27%. So we're getting close to the record efficiency of the solar cell in the world, right? And these are some statistics, and that's the efficiency, and that's again the post-mortem characterization. And to me, it seems like if you don't toughen the interface, it's like putting a wire on a conductor. And putting a toughening layer is like soldering it. Which is better? So it's like no-brainer to me. but it's very hard to convince the photovoltaics community that they should be thinking about mechanical properties or mechanical behavior to make their devices stronger. All right, so come to the second story. So the second story is about flexible solar cells. So flexible cells, as I mentioned, they're deposited at near room temperature and take only 500 nanometers, and therefore you can make it flexible. A 200 micron silicon wafer is not flexible. You can imagine, it just breaks into a million pieces if you try to bend it, right? So that's the advantage. Another advantage is they can be produced at a mass scale by roll-to-roll continuous process, right? And they have very unique applications. So for example, you can put them on tents and collect power. You don't need it on the grid. You can put them on drones. They're very lightweight, and that's all power. Power is the biggest problem in drones. The batteries are the biggest problem in drones, right? They can be put on wearables where you can collect indoor light. Because these are actually, I didn't say that, but the indoor lighting is very good here. They work very well in indoor lighting, right? That's what it says here, indoor and outdoor, what is for the Internet of Things powering. And then space, so you can basically, like an umbrella, you need large area, you cannot take this big umbrella in a rocket, so you basically take it as a closed umbrella and then you unfurl it in space, and it has to be flexible, of course, right? And collect a lot of light. Anyway, so a lot of people do the testing by bending this, okay? So the mechanical testing of this is done by bending many cycles, and basically people plot the remaining power conversion efficiency as a number of cycles and say that this is fatiguing. But there's a lot of problems here. I won't go into the details here, but the tests are not conducted properly, and this cannot compare it very well. And therefore I got involved in this consensus statement and by many authors. And basically we came up with some recommendations, is that you have to bend the solar cell to the entire radius, so everything is in the same stress state. Then the recommended strain, the number of cycles, and the choice of axis is also very important, because a lot of people were bending it in the wrong axis, because if the cracks go this way and the current goes this way, it doesn't affect your current. And so you see very high efficiencies. The current has to go parallel, perpendicular to the crack axis, right? And so on, but I won't go there. So this is our own solar cells. So the flexible solar cells are typically a little bit less efficient, about 21 to 2%. So these are our own solar cells that have been tested, and you test it under bending like this. So this is a torture device. And then you stop a few cycles and you measure the efficiency, and then you cycle it again, and you measure the efficiency in the flat state, so when the solar cell is flat. And so we use the rod here, mandrel, so that the stress is uniform over that area, right? But the mechanism of why this happens was not understood. And people basically said, well, they're brittle materials, and normal hand-waving explanation, which makes sense. You say, brittle materials, you get cracks, and the cracks multiply with number of cycles, and everything sort of decreases. And so my student was not satisfied by this, and this is where a lot of the curiosity of students really drives this. I was happy with this explanation. Sounds reasonable to me, right? And we even published papers based on this, right? And so he basically said, okay, I need to understand this. I'm going to go back to reduce the problem to the minimum level, okay? So there is something called TCO, transparent conducting oxide, on the substrate. That's the essential part, because it has to be transparent, light should go in, and it should be conductor to collect the charge, correct? And it's typically made of ceramics such as ITO, indium tin oxide, or IZO, indium zinc oxide, and there are other materials, right? They're very unique materials that can also conduct electricity and also transparent, right? Not very many materials do that. But they're all ceramics. They're all very brittle, right? And the polymer here used, what's called PEN, or polyethylene naphthalate, is extremely tough. So it's like your plastic wrap in your kitchen. it never fractures, it just stretches, right? But a ceramic is, how brittle ceramics are, right? And so when you bend this like this, it's very normal to see cracks in the ceramic. So this is the ceramic, and this is the bare substrate with no ceramic coating there, right? And so you don't see cracks here. And so this is very normal. Hundreds of papers are published this kind of work, and you normally think that yes, ceramic cracks, polymer doesn't crack because polymer is, compared to ceramic, is infinitely tough, right? But my student decided to do, so this is the toughness. So the toughness of PEN is about 55,000 joules per meter square. This ceramic is 5, perovskite is about 2, right? So they're all very brittle materials, right? So there's no perovskite here, it's just the TC or ITO, right? But what he did was, he did focused ion beam here. And what he found, to his surprise and my surprise, is that the substrate, which is infinitely tough, is actually cracked. Where there's no coating, of course the substrate is not cracked, which is what we see here. But here, by fib, you're able to reveal this coating is, the substrate is cracked. And from all my mechanics education, this didn't make sense to me. And kept me up at night because, so what's going on? And I asked him, this is the artifact, let's do it again. And by the way, these cracks are so deep, they're 25 microns deep into the substrate, almost 20% of the substrate. And so he did it on different substrates. This is ITO on polyethylene terephthalate. Then this is IZO, indium zinc oxide on polyethylene naphthalate. And this is Kapton, polyimide, indium tin oxide. All of them, some of them homemade, some of them are purchased. So we thought that commercial materials, maybe they do weird things there. But this universal phenomenon is where this infinitely tough substrate under a film is cracking like a ceramic. And so that's a problem, because if the substrate is like your foundation of your house, if it's cracked, you need to worry about it, right? And so that's what gave us a clue that is actually could be the problem of degradation of these solar cells, is that your foundation is degrading, so everything on top of your foundation is also going to degrade, right? Become unstable, right? And so why is this happening? And we thought, and Brown University is a very well known for mechanics. And so I talked to my colleagues, and nobody could sort of give me a good answer. And then finally I talked to another colleague, and and by the way, this is for the entire solar cell. So this solar cell has all the layers. This is the ITO, the tin oxide, the perovskite, the whole transporting layer, and the gold. And it's also cracked. So a lot of people publish this work, figures like this, saying, okay, this cracks, therefore everything is brittle, so everything cracks. But nobody says anything about whether the ductile substrate cracks, and does crack. And if you put perovskite just on the PN without any layers, even that makes the polymer crack. So it's really fascinating. Anyway, so we found a paper from 1978. It's the modeling paper, nothing to do with solar cells. And all it said is that when you have a stiff film on a compliant substrate, then when the crack approaches the interface, the stress intensity factor goes to infinity. There's a singularity because of the stiffness of the film. That's the only difference. The stiffness of the film is higher than the stiffness of the substrate. So at the tip, when it reaches the interface, it creates a singularity with such enormous K that anything would rip apart under that film, regardless of how tough it is. And so that's what we are seeing here. And so it's primarily due to this elastic mismatch, right? And so that gave us a clue. Of course, the TCO is 130 GPa, the polymer is 9 GPa, right? And therefore, that difference is why this cracking occurred, regardless of the toughness of the polymer. And this is driven by these intense shear stresses that occur at the point there. If we have a compliant film, low modulus film on a substrate, then actually it arrests. goes the other way, right? It doesn't, the film would not fracture, sorry, the substrate will not crack, right? So based on that, we created this design map. So I mentioned only Young's modulus, but there are actually other elastic properties such as Poisson's ratio, bulk modulus, and shear modulus go into the picture. And so this is called the Dunder's parameter, alpha and beta. So they're basically elastic mismatch, quantification. And so with the green, you're safe, substrate doesn't crack. If you're in the red, the substrate cracks, okay? And so you want to stay away from that. And so based on this hypothesis, we came up with a approach to mitigate this. So I'm an engineer. So yes, understanding is great, but what are you going to do about it? How is society going to benefit from your understanding? And so we always think about it that way. And so, okay, so using this map, we designed a mitigation strategy where we put an interlayer, which is lower modulus than the film and the substrate. And so when the crack comes from here to here, it's going from stiff to compliant, and so the crack will propagate. But now the crack is going from compliant to stiff because the interlayer is more compliant than the substrate. Now the stress intensity factor actually goes to 0 and the crack will not propagate. And so we chose PMMA, polymethyl methacrylate, which is about 3 GPa, the substrate is 9 GPa, and the film is 130 GPa, right? And so my student made these without the interlayer, of course, this cracks. With the thin interlayer, about 200 nanometers, it still cracks. But when you have about 300 nanometer interlayer, the crack stops. And of course, when you go to thicker layer, it stops. Then we use a different interlayer with PET, which is also lower than PEN, crack stops, right? And now we have a way to stop the substrate cracking and hopefully improving the reliability of the solar cells. Okay, and so I just have a couple of slides here. And so this is, so we measured the resistance of this ITO or IZO as a function of the number of cycles. And so over 10,000 cycles, you measure it in the flat state, the resistance goes from 0.1 to about 1,000. So 4 orders of magnitude increase in resistance with no interlayer, correct? And the reason this is happening is, the hypothesis is that when you bend it, the film cracks, the substrate cracks, then when you make it flat, the film comes together, there is contact, there's no infinite resistance, there is some conductivity, right? But because of the substrate cracking, every time you do this, it's not closing quite properly because you can get debris and the closing is improper. And this has been shown in other systems, in metals and things like that. And so therefore, the resistance keeps increasing with number of cycles because you cannot close, make the contact. The contact is improper. But if you prevent the substrate cracking, then you can actually have better connection between the ITO layers. And so that's what we show here. So you get 4 orders of magnitude change here, but with the interlayer, where the substrate doesn't crack, the resistance really remains almost the same over 10,000 cycles because the substrate did not crack. So whenever you made it flat, the coating came in contact to pass electricity, right? Anyway, so it has very broad implications because ITO on polymer is not only used for perovskite, but also organic photovoltaics, lighting, all the displays, touchscreen displays, they all have this ITO on polymer. Then you have these bending phones, Samsung phones, and Apple is coming out of the phone. You can look at the radius. We are bending this at 4 millimeter radius. That radius is 2 millimeters or 1.5 millimeter bending radius. The stresses there are enormous, right? So all these things have become relevant in these different kinds of applications. All right, so one last slide. What are the outstanding issues? The record efficiency that I showed you is for small solar cells. When you go to modules, which is what you would need in a solar panel, the efficiency is only 21%. Doesn't come near close to silicon, okay? And so scalability is important. So how can you scale this and achieve the same efficiency? Then stability is important, inherent stability. And then we talked about, okay, we didn't have a chance to talk about this, but these are dynamic solar cells compared to something like silicon. It has advantages, but it has disadvantages. So we're going to try and play on the advantages, but these things need to be solved, right? And then the environmental stability, so all of them have lead. And if some of the chemists in the room, they will know that each element has a unique position. Yes, there is the periods, but if you replace lead with tin, for example, it has two redox states and it readily oxidizes into the 4 plus. Solar cell is dead because it doesn't absorb light. It's different crystal structure, right? And so you have to worry about these things, lead especially. In utility scale, that's fine because actually there's more lead in silicon solar cells in the soldering than these because they are very thin. So, if a solar cell breaks, then the amount of lead that goes in is actually less than the naturally found lead in the soil. But people have perception, right? People say, no, lead is dangerous, right? And so utility scale, it's sealed off. Nobody can go in there and they can recycle it and everything else. But consumer electronics, things like tents and drones and things like that in people's hands, they don't dispose it properly. And so therefore you have to worry about that. So right now this European limit ROHS is like this. So if you have solar cells on glass substrate, it's actually under the limit because the denominator is the total weight of the device. But if you make it on plastic, it is way off. But right now ROHS is not enforced because it's renewable energy. So renewable energy technologies are exempt from ROHS requirements. But who knows, things might change, right? So we need to worry about those things. And then operational stability and reliability, as I talked a lot about that. So these are a lot of the outstanding issues. And then of course there could be new materials, new light absorbers that we don't know of from this millions of compounds, right? Anyway, so this is what I wrote in this review article, is that the price of widespread commercialization of the perovskite PV technology and the prospect of doing fascinating science along the way make addressing these challenges a worthwhile endeavor. So for any postdocs and students out there, or PIs who want to get into a new field, this is an exciting field, especially in Europe. In US, funding for renewable energy is down, but hopefully it will come back up again. And so if you're interested, I've written these review articles and some perspectives on mechanics and so on. And so that's the summary. I don't want to go into that, but that's my acknowledgement. That's my research group right now. It's Christina here. And so Christina actually worked with Rosalia and Angela in Sevilla, and she was a postdoc with me. Now she's left. She's gone to Georgia Tech. And so she contributed to a lot of this work, a lot of contributing collaborators. This is the funding agencies. And so I'm going to indulge a little bit in some nostalgia now. And so this is Rosalia and Nicholas in United States. And so that's Rosalia in 2004. She has not changed a bit. And this is my wife, and this is my son and his friend in Halloween. They were Halloween. And so actually Rosalia is also wearing Halloween pumpkins, right? And so this is a Christmas party, I think, at 2005. And this is a wedding of one of the students here, Ed and Michelle's wedding, right? It was Rosalia and Nicholas. And this is Rosalia's birthday party, 2006, the group. And this is a group photo in 2006. So with that, I'd like to thank you, and I'm happy to answer any questions.